Good evening to everyone. Let's continue our lesson with example 1, DC motor. Okay, let's take a look at example 1 question. It is a separately excited DC motor that has the following data. So it gives you kV, the motor constant, the VT, the armature resistance 2 ohm, VT 600 volt, and rated armature current is 5 amp. Okay, the question asking you to calculate the rated torque, which is TR, starting torque TST, and starting current IST at full voltage. Okay, and you need to sketch. One is calculate, and second sketch the speed current characteristic of the DC motor. Okay, so if you know me from previous subject, I usually prefer to start the solution or the answer with drawings or sketching the equivalent circuit of what is the particular motor that been asking you to solve. Okay, so now this is the equivalent circuit of separately excited DC motor. Okay, we have two circuit there. One is the armature circuit, your RA, your LA, your EA here, and your VA. Okay, and this one is the field circuit, VF, your RF, and your LF. Okay, so since the question is asking you to calculate the rated torque, you can just use directly the developed torque equation, which is the KVIA, similar that you have learned in the machine. Okay, KVIA, and since it's asking you for the rated torque, so for your current you need to use the rated value. And now we just can right away insert all the necessary value that given by the question. So the motor constant kV is 3 times by rated current 5 ampere. So the answer is 15 Newton meter. Next, the starting torque. Okay, so for TST, you can refer to the slide. Okay, for TST, we already derived the TST. Where is it? Not here. Okay, this one. You can obtain the starting torque and starting current by setting the motor speed to 0. Okay, so when the motor speed equal to 0, this is the motor speed equation. Set it into 0, and you need to rearrange this equation. For this one, since it's have parameter of IST, so you can rearrange this equation to have the starting current. And if you wanted to find the starting torque, so what you need to do is this one. Okay, replace this with T, right? T equals to KVIA. So when you rearrange IA, so it's T over KV. Okay, so now moment, I need to actually you are substituting this IA with this one, and from here the equation will become VT over KV minus RA, look at here, T over KV square. Okay, oh sorry. So from here now okay, you have the T here, torque here, and this torque is actually the starting torque when you set this speed to 0. So when you set the speed to 0, now it will become TST. It's similar with this one, and you can rearrange this T. Let's have derived it back, since one of your friend is asking about the derivation. So let's rearrange this T. So now VT over KV equals to RA TST over KV square. Okay, so we can cancel this square and kv, and we need this starting torque, so it's TST VT RA kv, same, right? Okay, so you can use you need to use you need to use this equation to calculate your starting torque. Let's go back to the solutions. So your TST is VT kv over RA, and you have your VT here and kv here and RA here. So just put the value. So 600 times kv is 3 over RA is 2 ohm. So now the starting torque is 900 Newton meter. And next for starting current, so IST, you can refer back to the same page of slide. So it's just a VT over RA, okay, terminal voltage, or VA over RA, the one that given by the questions there. Okay, so just put the value. It's 600 over 2, so it's 300 Newton meter. Okay, so now sketch the speed current characteristics. So when you need to sketch the speed current, so one axis is for speed, one axis is for current. Okay, you can use 2 units here since I'm using the omega symbol. So it's a radian per second, and this one is ampere. Or you can also use RPM, and I. Okay, so if you use M, you need to use RPM, and you need to convert the radian per second value to RPM value. Okay, alright, so let's take a look how to sketch. Okay, for speed, you need to know what is the no load speed value. So the no load speed value is VT over kV. So your VT is 600 volt over kV here 3 volt second, and you will have 200 radian per second. So let's say I just put this 200 here. So this will be your omega naught. Okay, and from this equation, it's derived when the speed equals to 0, right? And same goes to this one. It's derived, or this equation is exists when you set the speed of the motor is 0. So this value is when the speed of the motor is 0 here. Okay, this one is the motor speed become 200 radian per second. So let's say I just select any point, and it will become 900. Oh sorry, this one is current. So current, kita ambil current. Sorry, this one is not Newton meter, this one is ampere. Okay, so current, this one is current, it's 300 ampere. Okay, and next we can tak apalah. Okay, we can just draw a straight line from the no load speed to the maximum current. Okay, assume that this is 300 point. Okay, alright, next this one is speed versus current. So for speed versus torque, let's say I don't want to use the unit RPM, I just stick to the radian per second. So omega radian per second, and this one is your torque. Okay, so it's the same 200 here, so it's 200 your omega naught, and 1 point for maximum torque, since at this point is speed equals to 0, you will have your starting torque here. So this is your TST with a value of 900. Okay. TR, TST, I starting. Okay. Now you have two torque value rated and starting, and two value of current, starting current and rated current. So let's take a look what is the ratio of these two parameter things. Two parameters. So let's say this TST, starting torque, ratio with the developed torque, it is 900 with developed torque this one 15. Okay, so 900 divided with 15, you will have 60. So you can say that starting torque is 60 times larger than developed torque or rated torque. Okay, how about current? So now IST, I rated, okay, equals to starting current is 300, ratio with rated current here 5 ampere. Okay, and we make a division to know how much does it enlarge. Also 60, and you can say that the starting current also 60 times larger than rated current. Okay, so when you start, let's take a look on starting current. This one is your starting current. Okay, at no movement or no speed, when you start the motor with this 600, you bagi dia 600 volt. Okay, the motor already draw 300 ampere. Okay, however, this 300 ampere will not last longer, because as the speed is increased, okay, you increase up to 200, the no load speed, okay, it will reduce the starting current. So now from 300, let's say from here, from 0, previously is 300 ampere, and it will reduce to like 280 maybe. Okay, and then the speed started to increase from 50 to 80. So at 80, it started to reduce more the starting current, maybe like 250 ampere, until it reached a certain speed and current. Okay, so meaning of this rated current, you can draw one maybe here. Okay, let's say this is 5 ampere scale. Okay, so at this point, this is the motor speed, omega. Okay, motor speed. Remember, the motor speed equation consists of two terms, which is, you can use this one. Okay, the no load speed and the speed drop. Okay, so from this equation, this is the no load speed, and the speed drop is the slope of the line of the graph. Okay, and this is your starting current, as well as TST, because we know that as when torque is increased, torque and current have a directly proportional relationship for a DC motor. So when torque increase, current will also increase. So when we mention about its figure, it will also share the same characteristic within current and torque. So this one is for current. So when it's mentioned about torque, or when talking about its torque, it will also have the same figure of behavior. Okay, so that's for example 1. Okay, sketch the speed current. So the speed current is this one. Okay, speed characteristic of the DC motor. Alright, and you need to know, okay, when you start a motor, okay, without increasing its speed, okay, so the motor will draw this 300 ampere if it's contain this current for a long time. You know that what will happen, it will damage the winding. How? By heating. Okay, current tinggi, panas kan, okay, it will damage the winding, and thus it will reduce the lifespan of your motor. So we don't want this to be happen. So as much as we don't want it to happen, so once you start the motor, you need to make sure that the speed, the rotor, we started to rotate and spinning until it reach the dedicated speed of that particular motor. Okay, so that's all for example 1. Let's proceed with example 2. Okay, for example 2, assume that the starting current of DC motor in example 1 must be limited. So we need to limit this starting current. Okay, if previously, let me draw back the figure or the graph. Alright, so this is your current, this is your motor speed. Okay, let's say that this is the what we got previously, 600, 300. It's 300 and 200. Okay, so this one is 300 ampere and this one is 200 ampere. Okay, so now what does the question wanted you to do is limit this one to 6 times of the rated value. So previously we know that the rated value is here, it's 5M, right? Okay, so this limitation, okay, so now your IST must be 6 times I rated. Okay, so now it's 6 times 5, 30 equals to 30. So now maybe your 30 is around here. Now this should be your IST instead of this one. Okay, we need to have this new starting current. Okay, why does this example asking you to do this? Okay, if we look at example 1, kan I ada mention that bila initially when you start a motor and it give you 300 amp, you need to make sure that you will have to increase the speed as soon as possible so that you can reduce the current. Okay, that's another way to reduce the starting current is by you can adjust this terminal voltage. Okay, why? See this one, when you reduce this value, the starting current will also reduce because it's directly proportional relationship between starting current and terminal voltage. Okay, and another way to reduce this starting current is by adding resistance Ra on the circuit. Okay, and look at the same equation here. So when you add Ra plus Rf, okay, the higher the resistance value here, the lower the starting current. Okay, so the same concept. So now for example 2, it trying to show you how can when we reduce this terminal voltage, it can affect the starting current. Okay, example 2. Okay, now how much we need to reduce this terminal voltage so that the starting current can be reduced up to 30 amp or up to 6 times higher than rated value. Okay, So now what you can do is you already know the new starting current. So this is IST new. Okay, next we have IST equals to VT over RA. Okay, so since for this solution of example 2, our interest is only by reducing this starting current by modifying or adjusting this terminal voltage here. Okay, this is your VA, this is your VF. Okay, so now you need to notate that on your equation. So since this is IST new, you will have your new terminal voltage but with the same RA value. Okay, so now we have this one IST new is 30. So VT new, the one that we are looking the value, and we have your RA from previous example is 2 ohm. Okay, 2. So now rearrange the equation. 30 times 2, 60 volt. Okay, so with a 60 volt you will have new starting current here. And let's check on, does we have a changes on the no load speed. So the no load speed equation is VT over kV, right? VT over kV. So this VT is a VT new. So your VT new is here 6 over kV 3. So your new no load speed is 20 radian per second. Okay, so now say this one 20 radian, maybe somewhere here 20 radian per second with this one is omega not new. Okay, now you can draw one new line for the new starting current with a new VT. So this one, the original line is with VT 600. Okay, when we reduce the terminal voltage to 60 volt, it is found that you will have a new starting current with just 30 amp with initial or the no load speed with 20 radian per second. Okay, ini no load speed bukan motor speed. So motor speed, tengok sini, originally this is your motor speed, and if you reduce the terminal voltage, the starting current will be reduced, as well as the motor speed also will be reduced into this point. You kena tengok line ni, yang mana yang cross with the slope, that is your motor speed. Okay, what else you can conclude from this example is when you reduce the source voltage here, okay, when you reduce the source voltage, you can see that it will have the same slope, okay, of speed current. Okay, however, the no load speed will be reduced as well as the starting current. Okay, what else? Okay, and that's all for example 2, because dia nak new voltage source and sketch the new speed current characteristic. So this is the new voltage source and this is the new speed current characteristic. So be careful when the question asking you for a speed current, you must draw the speed versus current. If the question is asking you to draw the speed torque characteristic, you need to change it to torque. Okay, so that's for example 2, and I think it's satisfied for you to proceed with the lecture. Okay, example 1 done. You may also refer to the slide given by Madam Ash for group 2 and 3. Just the same slide, just I upgrade for my slide. Okay, before that, okay, speed control of separately excited DC motor. For a separately excited DC motor, for a given torque, the motor speed is a function of the following three quantities: the armature resistance, the terminal voltage, and the field flux. Okay, and by that, this is the equation of speed. Okay, this one is the same. It's just that they expand the kV. Sorry, what is it? This one. Okay, and you need to know that we have two: speed versus torque and speed versus current equation. For current, torque will replace by R, and you will have only one kV. You can also write like this: PT RAIA over kV. Okay, alright. From this equation, you can see that speed of separately excited DC motor can be controlled by 1. Adding an armature resistance. So armature resistance to originally here you can modify this equation. Now it become RA plus RA. Why? Because RA is placed in series with your armature resistance. Okay, so this is your RA, this is your VA, RA, or you can also, that's one, this one. Number 2, you can also for number 2, varying the terminal voltage. So let's say you have your circuit here. For varying terminal voltage, you only varying the terminal voltage without adding the additional resistance. So one at a time. Okay, so you only varying this VA. Your RA is still same, 1 RA, 1 LA. Okay, and number 3, you can adjust the field flux. So adjusting the field flux usually involve the field circuit. Okay, for this one, usually I put another color here. For number 3, we can adjust your field flux whether by adjusting VF or adding R here, RA on the resistance in series with the field resistance. Okay, that's one is number 3. Okay, we'll take a look on this method of speed control for a separately excited DC motor. Further, we'll look at this topic further or in detail in next class, our face-to-face, our online classes this Monday. Okay, this one. And where is it? And to end my lecture, asynchronous, let's do quiz. Quiz for week 2. Okay, what you need to do is find the motor speed for condition in example 1 and example 2 on a previous example, and conclude your finding regarding relationship between terminal voltage, no load speed, and speed drop. You may draw a graph to help your explanation. Okay, I will prepare the Google form link to upload your answer, as well as filling up your attendance, and the link will have a limited time. I will open the link with a limited time so that you have a limit time to cater quiz condition. Okay, I will tell that in your WhatsApp group for this quiz, and limitation of the time response to upload this quiz. So if you exceed the time that I set, so your quiz mark is not count. Okay guys, thank you very much for your attention. Assalamualaikum warahmatullahi wabarakatuh.